Okay, everybody. Welcome back to Concurrent Session 4, What's New in Research at Iowa State University. I'm Jake Seibert, and along with Carson DeMille. Our next speaker is Dr. Brett Ramirez, Assistant Professor in Agriculture and Biosystems Engineering. Brett is an Illinois native, calling Crystal Lake, Illinois his hometown. He attended the University of Illinois at Urbana-Champaign, where he earned his bachelor's and master's degrees in agricultural and biological engineering. He also was on the track and field team through hammer throw for Illinois. Ramirez says his interest in agricultural and biosystems engineering came from the need to produce safe and secure food. Dr. Ramirez's research and extension program focuses on developing sustainable livestock and poultry systems that are resource efficient and promote performance, well-being, and health. His specific research areas include housing, natural resource and energy efficiency, animal energetics, environmental control, and precision livestock farming. The goals of his program are to provide the science, solve problems impacting Iowa producers today, and develop new technology to meet the animal needs of both economically and sustainably. So the title of his talk today is Minimizing the Impact of Heat Stress on Pigs, Common Ventilation Errors, How to Correct Them, and How to Prevent Them. Heat stress continues to have negative impacts on pig performance across all stages of production, and this talk will first discuss practical methods to identify heat stress conditions and what parts of the ventilation system can cause problems. Then more detail will be presented on best management practices to reduce the impacts of heat stress and increase performance. So, Dr. Ramirez, the floor is yours.
Thanks, Jake. So as Jake said, today we're going to be talking about heat stress, the impact of heat stress, and then getting into kind of some different modes of cooling, how they operate, and what's kind of the best management practices and prevention strategies that can be taken. Then if I got a little time at the very end, since this is, I guess, on what's new in research at Iowa State, I do have a little bit of research update on some of the swine projects in Ag and Biosystems Engineering. So without further ado, impact of heat stress, I think this is pretty well known. It's, I think, gets reiterated all the time, but just to make the point, reduced feed intake, reduced growth performance, it's a welfare concern, it's a stressor, and it can lead to mortality. All things that are bad, and we want to avoid them, and as we see from finishing weight, this is from the pork industry analysis in 2015, we see in the late summer months, as you know, we currently sit right on the edge of June and July, and we start to see finishing weight start to decrease. Well below average, and we see average daily gain again dip well below average in those late summer months. We know it's an issue. Seasonal variability continues to be a challenge today, and you know, if you could increase that finishing weight 1 pound during those months, you could have an increase in $550 for every 1,000 pigs raised. So there's a lot of money on the line when it comes to decreasing the impact of heat stress. Also, looking at the impact on the breeding herd, it's a delayed response as those warm summer months going in, and you see the litters affected by boar fertility into the winter. So what is heat stress? You know, this is more from my engineer's perspective on the outside of the animal looking in. We have what we call as the effective environment. That's kind of the sum of everything around the animal. We'll get into more details, but that's what is all affecting the ability for that animal to lose heat. Because our job is to pull that heat away. Core body temperature, normal, around 39 Celsius for the pig, and then as you see, as it goes through the different zones of thermal regulation, core body temperature drops off when it gets too cold, goes up when it gets hot. So we have some heat production. This is essentially how much heat is the animal making, and kind of how much heat do we need to remove. And we have kind of different mechanisms that the pig can use to regulate itself thermally. So in the normal kind of thermal neutral environment, we have vasomodification, changing the opening diameter of veins, behavioral changes, so huddling, separation, you know, resting, standing, sitting, moving. Also, pelo modification, raising and lowering hair. Not a big deal, but it does add to the animal's ability to kind of cope with its thermal stress. Then we see on the heat stress side, increased vasodilation, pull as much of that heat away from the core body temperature as possible. Panting, so pigs, don't sweat, so they essentially rely on heavy respiration to reduce that heat. That respiration is essentially working like a big evaporative cool cell inside. They're using evaporation of water in the lungs to respire that air and cool themselves down. So that's important later on when we talk about cooling methods. So feed intake, as we know, decreases in heat stress. And so our kind of goal from the engineer's perspective on the ventilation system is to kind of maintain the animal in this kind of thermal neutral zone. It's a wide range. It's different for every animal. There's no set zone out there that's ideal, but be aware that it's changing. It changes per barn, per conditions, per everything in fact affects where this zone lines up for each animal. Heat stress is on the other side of that zone when it's too warm. The infective environments, too much heat is being added to the animal, and our job is to minimize that. So briefly on thermal exchange, as mentioned, pigs, just like all animals, us too, mammals, all homeotherms, we all strive to keep a constant core body temperature. That's as a result of basal metabolism, trying to obtain nutrients, heat increment from feeding, combating stresses, which can direct energy, which is also attributed to a poor environment. Either a hot and the cold size, and to kind of put that in perspective of how much energy heat is a pig producing. 220-pound pig at 61 Fahrenheit is around 867 BTUs per hour. And when you multiply that out by 1,200 in a room, that's a lot of energy being added to that room that all has to be taken out. So kind of briefly, an animal exchanges heat with its surrounding. Why does that matter? Because this is what kind of dictates what is the best way to cool pigs, and understand what mechanisms do you need to rely on that's going to take that heat away the most effectively. So we have 4 different modes. Conduction is through the floor, that's direct contact, or through any surface. We have forced convection, so think about high air speeds, essentially tunnel ventilation. As the air moves over the pig, it takes heat away. Natural convection is more during kind of a colder environment, and that heat just kind of naturally rises, as many of us have seen. We have evaporation. Think about panting as a mode of evaporation inside the lungs, or wet skin from sprinkling or sweating is one way to rely on evaporation. Then we have thermal radiation. A little bit harder to understand because it's just the exchange of energy with all of your surroundings. So as everybody kind of packs in close but not touching, you kind of feels warmer. That's thermal radiation exchange. Or if you're near like a cold window and you put your hand out and that window feels colder without touching it, it's another form of radiation. So what does this mean in terms of what are these? How do I understand what they are? So that's why all those modes of heat transfer all have correlations with different parameters, such as temperature, airspeed, which is a main driver of how do we understand how much forced convection heat can take away. Mean radiant temperature is with a black globe. It measures the surrounding surface temperatures. And we have evaporations driven by temperature, humidity, and air speeds. And I kind of put down for conduction, it's a little difficult to measure. It gets challenging with the pig's body temperature changing and let's say floor temperature changing, for example, and it's a little bit harder to estimate. So how do we quantify heat stress? So this is from my PhD research is put together the thermal environment sensor array, which basically combines the 4 measurements that describe all the different modes of heat transfer into kind of one package that is able to do that. So we have a airspeed sensor that measures airspeed around a big black globe. This is a 4-inch PV or plastic toilet float from Granger. It's cheap. It's better than buying a copper one, which is the standard method. We have just a regular temperature sensor and a regular humidity sensor, and then it's kind of packaged together that all runs back to a system for managing the data. So another way of thinking about this is how do we take those measurements and actually combine them into something useful? So this is a challenge I see with a lot of thermal indexes like temperature, humidity index, which only looks at 2 parts of the system when in reality there's really 4 different parts that are involved. So we came up with something called the house swine heat stress index. The paper is currently under review. That basically combines the 4 measurements on the previous slide, plus has an option for wetted skin. So if you want to see how is my system working even with sprinklers, it has the ability to adjust. Essentially, this index scales from 0 to 10, with 0 to 3 being the ideal thermal conditions, and then 3 to 7 moderate, and then 10 being very severe. So we kind of use this as a method of kind of quantifying and indicating how heat stressed pigs might be. So putting this all into something a little more practical. I'm going to go through kind of briefly these different cooling systems. First one being Airspeed by tunnel ventilation, evaporative cooling with evaporative cool cells pads, which is more an indirect cooling. Low pressure sprinkling, which is a direct evaporative cooling right off the skin of the animal. And then I'll briefly mention a little bit on floor cooling, as some manufacturers are having slats with circulating water. So the first kind of goal here is with airspeed and tunnel ventilation, is really to develop a high wind speed across the animal for increasing convective heat loss. So in the graph, I kind of have an example of our airspeed as it increases, and the effective temperature, which again is just kind of a way to combine the different modes of heat transfer into something kind of relatable. Now, 1 degree effective temperature is not the same as 1 degree temperature, just regular air temperature. That's kind of the combination of everything. So we see for our small 44-pound big, the effective temperature is much lower at, let's say, a typical tunnel speed around 350 to 400 versus a 220-pound pig. Smaller pig, smaller surface area to volume ratio compared to the bigger pig. So as I explained there, surface to volume area ratio decreases. This is an important part, especially on the very small end for weaned pigs. This is a critical aspect that has to always be considered, as those small pigs can lose heat so fast with the environment. Always great care is needed to make sure they stay warm. So what happens if the air temperature is 95 degrees, like it will be, I think, is it Saturday? It's supposed to get pretty hot here. Now what happens to the effective temperature? Pretty much the same. It drops maybe about 2 degrees. That's because once you start to approach the skin temperature of the animal, you can't pull heat from the animal anymore. There has to be a difference. And so at that point, you have to rely on something a little bit different than just tunnel airspeed to help cool the animal. So that's where usually the evaporation of water comes in, with either evaporative cooling or low pressure sprinkling. So another kind of common issue with tunnel ventilation is heat accumulation down the length of the barn. So this is just the modeled barn, assuming a certain amount of heat production per pen as you go down the length of the building, and kind of does it, and it kind of shows at different air speeds and how far away from the tunnel inlet are you, what's that increase in temperature. So we typically recommend about a less than 4 to 5 degree Fahrenheit temperature rise down the length of the barn, which assures adequate air exchanges in the building. So you look at 200 feet per minute, it's close to is that about 4 degree temperature rise at about only 150 feet. Looking at, most buildings being in this range, right about 400 feet, 2 meters per second is kind of the common goal. Versus, you go up to 1,000 feet, you can keep it under 4 degree temperature rise down the length of the building, but at what cost on your fans, and static pressure across the building envelope. So this is kind of a quick analysis I put together. I was trying to think of, sorry, blowing with the mic. Trying to think of how do you translate into what if you want to add one more fan? Is it worth it? What's my benefit for adding a fan? So I kind of made a few assumptions on cross-sectional areas, fans, static pressures, fan efficiencies, run times, electricity costs, just to kind of see what does it take to really build up until you get to, if you're sitting at 314 feet per minute of tunnel airspeed, what if you want to go up another 50 feet per minute and so on? At what point do you balance tunnel airspeed versus cooling benefit and average daily gain. So I have this in terms of a heat loss benefit. I need to put in more in terms of an animal performance benefit. But essentially, that benefit exponentially decreases, and there's a point where you can keep adding airspeed and you just don't get any more cooling benefit. It has to do with the shape of the animal and how much heat they make. Versus same with fans, you can keep adding fans, but that cost to operate those fans grows exponentially as your static pressure increases, which drives your fan capacity down, which decreases your fan efficiency. And so you have to keep adding fans. So there's kind of a tipping point somewhere in here where you're exponentially increasing power and money to operate those fans, but not really getting the benefit in cooling the animals. So common errors is high temperature rise, so greater than 4 degrees Fahrenheit. Too much airflow restrictions commonly seen, not enough tunnel area opening, insufficient fan capacity causing that increase in temperature, high animal density resulting in a lot more heat production than what was maybe designed for. Solar radiation, a lack of insulation in the ceiling or compressed insulation where it's no longer providing the insulated value that it was intended. Fan stage settings sometimes get off and need to be reset and refigured out for what the temperature differential needs to be. Sometimes fan shutters not fully open or dirty when they're just flapping and not well pulled open is usually an indicator that they need to be cleaned in order to get that fan capacity back up. So how do we prevent it, or how do we understand if we have a problem? Measuring. You don't know till you measure. So you can measure temperature down the length of the building, which most sensors are already there if you can pull the information off the controller, or physically walk down the barn with like a Kestrel meter or something that does airspeed, temperature, and humidity is a pretty easy, fairly inexpensive way to get some feedback on what's going on in the barn. Verify airspeeds at the tunnel inlet and also about 5 to 10 feet from the sidewall. As that air comes down through the tunnel, it accelerates in the middle, so there's kind of you want to make sure you get at the right spot on the cross-section of the barn to make sure you're getting something reflective of what the pigs are seeing or experiencing in the room. Checking variable speed setting controls, make sure everything's lined up right. And then verifying tunnel curtain opening and static pressure and temperature, so making sure there's sufficient, that tunnel curtain's opening enough when those later fan stages kick on, so there's not too much static pressure, which is decreasing capacity for the system. So moving away from tunnel, now we'll go into evaporative cooling. So kind of briefly, how does an evaporative pad work? We have air at a certain temperature and humidity that comes into the pad. That temperature decreases as it exits the pad, and then consequently the humidity goes up. That water evaporates on the pad itself, and it's pulling energy out of the air, therefore it's decreasing the temperature, but as the water evaporates, it's got to go somewhere, and it goes into that exiting airstream. So what's the potential of evaporative cooling? It's quite high if you're in a hot and dry climate. Arizona, evaporative cooling has immense potential. Compared to somewhere warm and humid, you only have the potential to reduce a couple of degrees depending on the conditions. But sometimes that might just be enough to reduce heat stress. So it's a balancing act. So just kind of to see some different areas and what the potentials are is like Amarillo, Texas, can reduce 10 to 15 degrees Celsius, so in the 15 to 20 Fahrenheit versus the Yucatan Peninsula, hot, humid. Also, the other thing to think about is nighttime. As temperature decreases at night, humidity tends to increase, and then kind of the effectiveness of the cooling cell can decrease during nighttime conditions. So what goes into cool cell efficiency? So this is important when it comes to maintenance and getting the most out of the cool cell. Cool cell efficiency is really a function of air face velocity across the cool cell and kind of the width of the cool cell, how thick it is. So if you look at this, 24-inch cool cell is close to 97% efficient, but that's a 2-foot thick cool cell, and that's just impractical when it comes to implementing, because if you look at a 24-inch thick cool cell at 400 feet per minute, the static pressure is over 0.35, which is just insane. The amount of fan capacity to pull air through that would just be it'd be unrealistic. So looking at the 6-inch cool cell, pretty common, right around the 75% efficiency, and most people operate right around the 400 feet per minute, which is a reasonable 0.06 inches of water across them. So other common errors, pad streaking, usually an indicator of poor water distribution, and that could be a result of water pressure, clogs, leaks, etc. Improperly sized pumps that aren't getting circulating the water to the different nozzles fast enough, clogged strainers that need to be emptied weekly, pad cleanliness, poor water pressure, poor water quality, bleed off or treating the water helps to improve quality. So what can you do? Just clean the strainers, clean the pumps, clean out anything that needs to be washed, verify, go out and inspect the pad. Is there good coverage? Is there streaking, no streaking? You can verify, again, with a Kestrel meter, face velocity. So this shows kind of an old pad at about 265, and I think on a brand new pad, it goes up to 875. So less restriction, more air can flow through, improve the efficiency, and help improve the cooling. So now I'll go switch on to sprinklers. The goal here is to wet the animal's back, move air across the animal, and then let that water evaporate. So as the liquid sits on the skin of the animal, that as it evaporates, it's going to extract the heat out of the animal, and then the combination of the temperature, humidity, and airspeed over the back of the animal will kind of dictate how fast that water evaporates and how much cooling potential there is. So if we think about when you evaporate water, the amount of energy to get that water to change phase from a liquid to a vapor is about 1,000 BTUs per pound of water. So there's an immense potential of removing heat from our high heat producing animals. So what is this potential in watts? So looking at kind of different air speeds, as airspeed increases, you're able to increase that potential, and kind of to show at different temperatures what that potential is. So you see at 95 degrees Fahrenheit, the potential to lose heat is actually less than 77, which most people would think, well, it's hotter, doesn't it going to evaporate faster and pull more heat? Not quite, as there's the capacity in a cooler air. You have the ability to utilize a wider range on the vapor pressure gradient compared to hotter air. So the other thing that goes into this is wetted area. So this is only for about a 10% wetted area versus a 20% wetted area. So again, putting more water on the pig can pull more heat. So looking at kind of thinking about what are common problems in using sprinkler systems is, the lack of information on what is the relative humidity in the room, how much moisture is in there. That high humidity is going to lead to insufficient evaporation. I mean, if you go outside today, it's muggy, you can just tell water's just not evaporating. So you need more time on the off cycle for the sprinkler. Another scenario is the water evaporates too quickly. It could be a dry day, and you actually can shorten that off time to actually improve the cooling. The sooner you can get the water dried and put more water back on, the more cooling you can provide. And one other scenario is low airflow. So with the lower airflow, less heat is pulled away, and the pig actually needs more time. It's hard to kind of judge all these factors without having knowledge of what's going on in the room. So common errors, again, kind of similar to the cool cell since they both run on water. Clogged strainers, poor water pressure, making sure those nozzles fully get spinning and can throw water. Missing sprinklers, so the missing sprinkler that just has a jet that shoots straight down is not helping. It is great for an enrichment, but it does not provide much cooling. Insufficient pen coverage, make sure the pigs can actually get to the water. If they do need to move around and get to it, they have the ability to get wet and get cooled. And directional sprinklers, again, it doesn't, like the jet shooting down, if it's pointing at the wall, it doesn't help too much. So kind of just to show what how much cooling can be. So here's a picture kind of before the sprinklers were turned on. And after turning on the sprinklers, you can see the significant, 3 Celsius decrease on skin temperature, and see the nice wetted area on the backs of these pigs. as they got wet from the sprinkler. So Ben took these pictures, so give credit to him for good camera work. So the last one is just kind of floor cooling. Real quick, kind of what matters here is core to floor temperature, so how much heat can be exchanged from the core of the animal down to the slats. Contact area, thermal conductivity to the floor, concrete versus plastic. Supply water temperature, if the water's coming in too warm, you can't really move too much heat. And then heat accumulation. As that water snakes through the system, it's going to build up heat as it pulls heat off, so making sure that water can get refreshed and cooled back down. So kind of the key take-home points on this, on cooling. Air temperature maintenance is critical, but it's not everything. Airspeed control alone is also insufficient. There's the combination of everything, and evaporation also needs to be considered as well. So use the pigs as feedback. Do they look comfortable? They're usually the best sensor and best indicator in the barn, better than anything digital. Understand how that cooling system removes heat. When you have the comprehensive understanding of the different parameters, it helps drive which cooling system is going to work best in my climate, in my facility. Understand the mechanical aspects, pumps, strainers, fittings, nozzles, everything that goes into it to make sure everything's operating the best it can. And I like you don't know till you measure, and it helps provide information. So now I'll quickly run through, I think I got 5 minutes-ish. On a couple examples, or a couple research projects going on at Iowa State in our department. Enhancing the health and well-being of pre-weaning piglets. This study is done by Suzanne in the audience, led by Dr. Shin, and looking at evaluating the impact of different farrowing crate sizes and layouts with 1 or 2 localized heat sources on pre-weaning piglet health and mortality. We're also quantifying postural behaviors as the sow is affected by those crate sizes and heat lamp layouts, and then looking at the relationship of surface temperature piglets and their health status. So quickly, we have a Connect camera mounted over 60 crates that's doing depth images, so you get a 3D view of each of the sow and her piglets. There's also a digital image as well. So we have 3 different stall layouts, all in SI unit, so I'm not going to be able to convert those that fast in my head, sorry. And looking at sow posture, lying, sitting, standing, kneeling, and then behaviors such as lying on the left or the right side, and then udder back or facing a heat lamp. And we're then also looking at the piglet distribution within the crate. So do they tend to certain areas more often, or are they switching between areas, and what's the frequency in which they do that? So kind of give an example of what one of these posture budget looks like. We have the breakdown of the posture between sitting, standing, kneeling, and lying, and the different percentages of the day. And we also have the crate broken up into the different zones that the piglet might be in. And so the question is, what do these behaviors and actions mean towards pre-weaning mortality, and what's their implications, and what can we find from this information? Another project also with Suzanne and Dr. Shin is looking at sow space study, determine the commercial sow's static and dynamic space requirements while housed in a pen. Again, using a Connect camera, you get a digital and a depth image, as you kind of see here. And that can be processed into kind of a nice picture that gives a good outline of the sow and her shape. So standing, looking at the length and the width versus lying, length and width, and then also looking at the space required when the sow gets up or lays down, or when it gets up. Then my project that I started at the tail end of last year is designing a novel cooling control algorithm for operating evaporative cool cells and sprinklers. So basically this is trying to take in all the climate data and figure out what's the best times to run the cool cell. If it's even good that day, there's some days where it's utterly ineffective to turn them on. And also looking at trying to find the optimal off time for when sprinklers are on. So this is up in northeast Iowa, a quad barn set up with our 2 treatments of where we're going to use the cool cell on this side and then sprinklers on the 2 south rooms, and that's actually about to get started next week. So we're going to be doing animal performance and also evaluating the effectiveness of my programming capabilities. So kind of an example from this barn, we have our ambient data, and then we track temperature and humidity in the attic, and then as it comes through the inlets, we have 3 of our thermal environment sensors array looking at the total environment. So kind of taking a nice hot and dry day in northeast Iowa, see a good drop in air temperature as it goes through the cool cell, picks up some heat back into the room, and that comes out as, effectively 10 degrees cooler with some airspeed, so a pretty nice environment. But, just to note that it's still at about an 80% humidity. Whereas if you get to a hot and humid day, coming out of the cool cell, it'd still get a nice about 10-degree drop, but by the time it warms back up in the room, you've only dropped about 1.5 degrees Fahrenheit, and you're still sitting about 70 to 80% humidity when, it's still at that temperature, the pig's relying on panting and evaporation in its lungs, so that higher humidity can cause issues with the pig trying to cool itself. So kind of using the house swine heat stress index value there of about 3.7 in that conditions and about 7.3 in this condition. So may have been worth just leaving the cool cell off that day to reduce heat stress. So that's all I have. Hopefully you enjoyed it and got some updates on research and learned about cooling. So thank you. Yep.
So we do have time for questions. Yep, go ahead.
3 to 4 to 600 feet per minute, is that right at the wall opening, or is that more towards the middle of the barn?
Usually 400 feet at the tunnel opening, and then about 5 to 10. You should be able to maintain that same airspeed down the length. There's some obstructions and stuff that'll kind of decrease it a little bit. Usually it's the design values at 400 at the opening.
Even from inlets? Ceiling inlets? Is that what you're aiming for?
Ceiling inlets, so during like a mild to wintertime, it's more at the 800 feet minute range to get a proper jet throw from the inlet. It's 800 to 1,000. There's several factors in there, but.
I drive by several finishers and I see them in natural ventilation with pit fans running. What's your opinion on that? I think it's a mistake.
Yeah, that's a challenging one. It's tough to say. It's hard to think about the pressures in the room. Is there the air fighting those pit fans? So that's kind of what I'm trying to think. Is it, if you're moving enough air through, is it actually fighting the pit fan, or is the pit fan still doing a little bit? Is it better than nothing? I guess that's my question. It could be doing enough to make it slightly better, so it could be worth it, but I think it's a toss-up. I think it's pretty debated, so I'm not sure if I have a good answer.
Okay, on that same question, in tunnel ventilation.
It's the same thing. That's kind of, my thought is the tunnel fans, they're much bigger. They're going to be overcoming the pit fans' ability to pull any air out. You're fighting, think about small little pit fans fighting, a massive 52-inch, 6 of them running. But is running the pit fan better than nothing? It's tough to say. It might just be doing a little bit to pull some of that gas off the headspace and out. But my thought is pit fans probably losing the battle at the end of the day.
If no more questions, we'll move on to the next speaker. Let's thank Dr. Ramirez again.